Hi guys, welcome back to EasyChem videos. In this video, I'm trying to explain to you how to calculate enthalpy change of reactions. When we calculate enthalpy change of reactions in a question paper, you may get so many different types of enthalpy changes. One example is formation enthalpy values. In some of the questions, we have combustion enthalpy values or bond dissociation enthalpy values. And at times, there are a mixture of enthalpy values that I have shown as various delta H reaction enthalpy values. Whenever you carry out an enthalpy change calculation, we have to do it according to Hess's law. Hess's law tells that the overall enthalpy change of a multi-step chemical reaction does not depend on the route. It does not depend on the number of steps or the paths taken. In the exam, if a question is about defining Hess's law, you can simply write this. Now, we can show Hess's law in other way also, where we say delta H is equal to summation of delta H. N is to show the number of steps involved. So where delta H is a heat absorbed or evolved, and summation of delta Hn is a sum of heat absorbed or evolved in the individual n step of the reaction. Now, this method of calculating enthalpy change has a special name also. Actually, we can identify this method as calculating enthalpy change of a reaction using various enthalpy values. I call it simply this calculation method, equation rearrangement method. These calculations are done using a simple method which can be known as equation rearrangement method. Why? Because we simply rearrange equations to arrive at our work, to do the final enthalpy calculation. Now here rearrangement means we may have to multiply an equation by a value. In equation rearrangement method, we find ways to rearrange given equations and enthalpy values to work out the equation for which the enthalpy change of the reaction is asked. It means you have been asked to find out the enthalpy change of a reaction. To help with this, there are some other equations also given to you. So we are going to find out the enthalpy change for the reaction given the using the given enthalpy values. This given enthalpy values, I call them various enthalpy changes. So we had to modify these equations to get the final equation. And finally, enthalpy values are also rearranged to calculate the enthalpy change in the same manner. If I talk about it, with more details, we'll read this first. It is important to remember in these calculations that whatever the changes done to an equation must also be done to the enthalpy changes also. It means if a reaction equation is multiplied by an integer, the enthalpy value of the reaction is also multiplied by the same integer. If an equation is inverted, the sign of the enthalpy change also must be inverted. For example, positive enthalpy goes to negative enthalpy. Negative enthalpy goes to positive enthalpy. Likewise, it can be explained in a very, very simple manner. To understand this concept better, we are going to discuss one example. In this example, iodine trichloride, ICl3, is made by reacting iodine with chlorine. If you react iodine with chlorine, we can get ICl3. We can call it iodine trichloride. It's a solid. To do this work, there are two reactions. First, iodine solid can react with chlorine to produce 2 iodine monochloride. enthalpy value is given for that. Afterward, this iodine monochloride is reacted with chlorine more to produce ICl3. By using data above, what is the enthalpy change of the formation of solid iodine trichloride? We don't have that equation. However, question says we had to find out the enthalpy change of formation. What is formation enthalpy? Formation enthalpy is the energy change involved when 1 mole of a substance at its standard physical form. There should be only 1 mole. So 1 mole of the substance should be at its standard physical form, and it has to be produced by its constituent reactants at their standard physical form. Accordingly, ICl3 solid formation enthalpy can be written like this: half iodine solid plus 3/2 chlorine gives ICl3 solid. Let's see how we can find out the enthalpy change for the formation of this particular compound using the equations given. Here I have taken equation A and equation B again. And we want to find out the enthalpy change for this reaction, which is given in yellow. See, I have circled iodine solid in the yellow equation. Iodine is on the left-hand side. Similarly, look at equation A. In A also, iodine is on the left-hand side. If substances present in the balance equation, final balance equation, are present in the given equations on the same side, it means we have less trouble. You know why. Focus on this again. In both A and B, we have chlorine on the left-hand side. There are 2 chlorine. And in our yellow equation also, we have chlorine on the left-hand side. Therefore, remember, we are trying to get this equation by adding A and B together. When you add A and B, we must get this equation C together. So what we do is we add A to B. But there's something else over here. When you multiply A to B, B is multiplied by 2. What's the meaning of it? It's because of this. In this equation, the yellow equation, showing formation of ICl3, we have only I2, Cl2, and ICl3. See, in the equation A, we have on the product side ICl. But this ICl is not present in the final equation. So when A is added to B, this ICl must cancel out. Therefore that, on the second equation, we have ICl on the left-hand side. When you add the A to B, the right-hand side 2 ICl must be cancelled by, in the equation A, must be cancelled by the ICl in the equation B. But you can't do it. Why? In the equation A, we have 2 ICl. In the equation B, we have 1 ICl. So if you want to cancel ICl by adding A and B together, we have to get 2 ICl to the equation B. So we multiply that equation by 2. So when you do it, you get I2 solid, here I2 solid. We have 3 chlorine here in the final equation. Why 3 chlorine? Because when you multiply B by 2, we get 2 Cl2 plus 1 Cl2, we get 3 Cl2. And then we have 2 ICl because we multiplied B by 2, so this becomes 2 ICl solid. Similarly, we have on the product side 2 ICl and ICl3 also, twice. Now we can cancel similar substances on the left-hand side and right-hand side, and we get the final equation, which is the equation C, where we have I2 plus 3 Cl2 going to give 2 ICl3. One more thing you must remember. Here in the yellow equation, there's only 1 ICl3. But in this equation C, we have 2 ICl3. So it's okay. We will go ahead with the work, get the value for the enthalpy change for C. But because C equation has 2 ICl3, but my standard equation has 1 ICl, the answer you are getting here can be divided by 2. So here, the enthalpy change for the above reaction means reaction C is plus 14. How do you get plus 14? Because equation A has plus 14. Plus, second equation has minus 88, but because we multiply that by 2, it should be negative 88 by 2. Total answer is going to be 166 negative. But the equation C shows the enthalpy change for the formation of 2 moles of HCl3. Hence, by dividing negative 166 by 2, we can calculate the enthalpy change for the formation of ICl3 as negative 83 kilojoule per mole. This is quite a big method work out, but then it's not very difficult to understand how the things happen in this equation. So we can improve the skill of calculating this sort of problems by discussing another example. In this example 2, again, see, there are 2 equations given, equation A and B. What is the enthalpy change of reaction delta H of another equation is given, equation C. We have to find out the enthalpy change for this reaction C using the equation A and B. In A, sulfur reacts with oxygen to give sulfur dioxide. In equation B, sulfur reacts with 3/2 oxygen gives sulfur trioxide. How are we going to use these two to produce the enthalpy change for the equation given there, which is reaction C? We have done one example. So according to the discussion we had with the first calculation, when we add the reaction A and B together, of course with needed modification, the reaction C has to be obtained. We'll see whether we can do it. Make sure to do the same modification to enthalpy values also in order to calculate the enthalpy change of the reaction C. I will try to understand this. Since sulfur dioxide is on the left-hand side of the equation C, what am I talking about? Sulfur dioxide is present on the left-hand side of the equation C. And also, sulfur dioxide is on the right-hand side of the equation A. When we add A and B together, you can't have sulfur dioxide on the right-hand side because in the equation C, we have sulfur dioxide on the left-hand side. So we have to invert the equation A. When we invert the equation A, you have sulfur dioxide gas giving backward reaction, sulfur solid and oxygen gas. See, the enthalpy change negative 297 has become positive 297. Now that is equation D, which has been constructed by modifying equation number A, equation A. We'll go further into this calculation and see what is there first more. Now go to the next point. Since sulfur trioxide, see, sulfur trioxide in the equation B is on the right-hand side. In the equation C also, it is on the right-hand side. So if you add A to B, sulfur trioxide will come to the same side as in equation C. So here I'm telling that since sulfur trioxide is on the right-hand side of the equation B and C, we don't have to invert the reaction B. So simply we add B and D. B is this one, D is this one. We have from reaction B, sulfur and 3/2 oxygen. Here, sulfur, 3/2 oxygen. And to that, we have to add the reactants of equation D, sulfur dioxide gas. Arrow. From the equation B, we have sulfur trioxide gas, here it is. And from the equation D, we have sulfur and oxygen. Sulfur and oxygen. If you analyze this equation, you can't consider this as a final equation because we have similar things here on the left-hand side sulfur, right-hand side sulfur. Left-hand side oxygen, right-hand side also oxygen. So we have to cancel out similar things. How can we do it? The first thing is sulfur can be cancelled out in that manner. And next one, We cancel this oxygen out on the right-hand side completely with these 3, so we get half oxygen here. Half oxygen means 1 oxygen. Half O2 means 1 oxygen plus 2 oxygen. You get 3 oxygen on the left-hand side. The right-hand side also we have 3 oxygen. At the same time, at the enthalpy values of B and D also, B is having negative 395, D is having positive 297. Value is going to get U260. But what is this 260? It is to obtain sulfur trioxide 1 mole. But in our equation, there are 2 sulfur trioxide. So this negative 260 should be multiplied by 2. However, negative 260 kilojoule per mole has been calculated for the formation of, it should be 1 mole of sulfur trioxide. But the reaction C over here, shows 2 moles of sulfur trioxide. Hence, the final answer is calculated by multiplying negative 260 by 2. Hence, the final answer is given as negative 520. Should be negative 520. Please consider this as negative 520. That's your answer. Now, in this example number 2, there's more work than in example number 1. But if you go through once or twice, understand this concept is pretty simple and easy. We can probably go to another example number 3. In this, we have 3 equations given. Using these equations, we have to find out the enthalpy change for this reaction D. Now, there are 4 equations given. Using equation A, B, and C, we have to calculate the enthalpy change for reaction D. Again, before we go ahead any further, we have to analyze the reactants and products on the equation D, and accordingly, how are they available in given equations A and A, B, C, we had to take into consideration. So observe well. We are going to the first point. Equation A, I'm just telling, equation A is inverted. Why do you have to invert? Because you can see in the equation D, we have carbon monoxide on the right-hand side. But in the equation A, we have carbon monoxide on the left-hand side. So if you invert the equation A, we can bring carbon monoxide to the right-hand side with oxygen, of course, and carbon dioxide will come to the left-hand side. So here, equation A is inverted because carbon monoxide is on the right-hand side of the equation D. In equation A, it is on the left-hand side. So by inverting, we can bring the carbon monoxide to the same side as in equation D. So here is that equation. Carbon dioxide gas gave half O2 plus carbon monoxide. I consider that as equation E. Enthalpy change is positive 283. In the first equation A, it is negative 283. Now it has become positive 283 because we inverted the equation. Now we go to the second point. See, just look at this first. In the equation B, we have hydrogen on the left-hand side. And equation D, also hydrogen is on the left-hand side. So I don't think we have to do any change to reaction B. So it's given under B2. H2 is on the left-hand side of both reaction B and D. Hence, the equation B is not inverted. You take it as it is. And go to the third point. Look at equation C and D now. In equation D, we have H2O on the product side in gaseous form. But in equation C, we have H2O gas on the left-hand side. So we have to multiply, we have to invert that also to get this equation C. H2O liquid goes to H2O gas. I consider this as equation E. For that, enthalpy change is positive 44. Because equation C is having negative 44, when we invert it, we are going to get positive 44. We inverted A and C, but we didn't invert B. Now we have to add the equation B to D, not to D, equation B to E and to F. Finally, add the equations as shown, B plus E plus F. See the values, negative 286, negative 283, plus 44 is going to give 513, answer is plus 41 kilojoule per mole. Here I have not done the adding part. We can add them and see whether it works or not. We discussed 3 examples and we got the 4th example. The enthalpy changes of 2 reactions are shown here. Potassium carbonate plus HCl giving potassium chloride, water and carbon dioxide, for which the enthalpy change is coming as negative 34. And second equation, potassium hydrogen carbonate plus HCl giving KCl plus water and carbon dioxide. For that also enthalpy change is given, it is plus 32.8. Now considering these two, calculate the enthalpy change for the given reaction. Observe the 2 reactions A and B to analyze the amount and relative position of reactants as I did earlier, and products compared to the reaction C. How can we do this work? See, we have potassium carbonate on the left-hand side in the equation A. Potassium carbonate. K2CO3 is on the right-hand side of equation C. Okay. In the equation 1, it is on the left-hand side, but potassium carbonate is on the right-hand side in equation C. So what should you do? We had to invert the equation A. Hence, the reaction A is inverted. Now, KCl aqueous plus H2O plus carbon dioxide giving K2CO3 and 2HCl. See, I have changed the enthalpy change also from negative 34 to positive 34. And second one, there are no HCl in equation C, but HCl is there on the equation A and equation B. No problem, because when you invert this equation A, HCl goes to the right-hand side. And in the equation B, HCl is on the left-hand side, so HCl will cancel out. But when you invert A, 2 HCl go to the right-hand side. But in equation B, we have 1 HCl. So what do you think we have to do? We have to multiply second equation, which is B by 2. So HCl also will become 2. It will get cancelled with the equation, HCl in the equation D, I have written here. So second point says there is no HCl in the equation C. Yeah, I can see that. But HCl is seen in both equations A and B. Yes. Hence, when you rearrange the equation A and B, the HCl should be removed. Hence, the reaction B is multiplied by 2. Reaction 2 is multiplied by 2. And then, when you multiply the equation B by 2, I get 2KHCO3, 2KHCO3, 2HCl, 2KCl, 2H2O, 2 carbon dioxide. Enthalpy change is positive 65 because here in this equation B, it is positive 32.8. When you multiply this equation by B by 2, enthalpy change also multiplies by 2. So I have made changes to A and both B and obtain equation D and E. When you add D and E, we can probably get the equation C. Now add equations D and E together and also their enthalpy values here. This is quite confusing to look at it. See, in the equation E, we have 2 KCl, 1 H2O, 1 carbon dioxide. Here, 2 KCl, 1 H2, 1 carbon dioxide. And from the second one, 2 KHCO3, 2 HCl. And on the product side, from equations D, K2CO3 is here, 2 HCl is here. From the equation E, 2 KCl is here, 2 H2O is here, 2 carbon dioxide is here. And you can cancel out. How? 2 KCl on the left-hand side and 2 KCl on the right-hand side will cancel out. And then on the left-hand side, we have water, 1 water. On the right-hand side, 2 water. So 1 will cancel out, 1 will remain. And then carbon dioxide is on the left-hand side. There are 2 carbon dioxide on the right-hand side. So 1 carbon dioxide cancel out, 1 carbon dioxide. And then one more thing to cancel out. 2 HCl cancel out with 2 HCl. And when you cancel out these equal, similar things on either side of the reaction, we get the final equation 2 KHCO3 giving K2CO3 plus H2O plus carbon dioxide. Isn't it the same as the equation C? Yeah, that's the same thing. So in order to get this, what did we do to the equations? We are going to do the same thing to the enthalpy changes also. Now D enthalpy change is plus 34, E enthalpy change is plus 65. Because we add D and E together, we add the enthalpy values also in the same manner. 34 plus 65.6, we get 99.6. Lengthy 4 examples. If you study this very well, you should be able to carry out any calculation that whatever the question you get in your paper. So that's one example for you to try at home. And there's another example for you to try at home. When you do these calculations, you definitely have to find answers also. Here are the answers. You can just check whether you can do this work. First, practice the 4 questions given under examples plus 2. 6 questions. If you do this work with real interest, it will be very easy to understand this concept. However, that's the end of it. Thank you very much for watching the video.